Okay, so we are starting. So good afternoon, PCS members and friends. Today we are having a seminar by Dr. Shivalika Sharma about electron correlations in breathing Kagome metal iron tin. And I will also be a scientific host today, so I will present our speaker. So Dr. Sharma studied at University of Delhi, and in 2014 she became a Master of Science in Chemistry. From 2015 to 2020, she did her PhD in chemistry at University of Delhi. And the topic was actually, I think, very related to physics because it was about multi-electron quantum dots and hydrogenic systems in magnetic field. So also she has a list of jobs, but among others, I'd like to say that she was a postdoc fellow at APCTP with Professor Igor Dimarko she worked. And also she worked with him recently in Nicolaus Copernicus University from 2023 to January 2025. At the moment, she has 19 publications and also several awards. So let us welcome our speaker. So please, the stage is yes. We have an hour of 1 hour. Yes.
Thank you for such a nice introduction, and I also thankful that I am able to present my work in front of you all today. So the topic of my today's talk is exploring the effects of electron correlation in breathing Kagome metal Fe3Sn system. So before diving into the technical part, this is the outline of the talk. First, I will give a brief overview and spend a few minutes on the explaining about the Kagome lattices and why I chose this specific class of Kagome family, that is Fe3Sn family. And then I will discuss my core results of the 3D Fe3Sn system by analyzing the band structure and the magnetic exchange interactions. That I got through the ab-inito methods of DFT and also beyond DFT going for DFT plus U and DMFT. Then I will summarize the concluded remarks and what can be the possible future direction based on the work that I did in this system. So in recent years, condensed matter physics has been deeply influenced by majorly two themes, that is band topology and correlations. So band topology globally refers to the electronic bands that we see and where it is not just limited to the energy, but how is wave function connectivity to in the momentum space, which give rise to many robust surface states like Berry curvatures and Hall effects. And on the other hand, when we look at the electron correlation, when electrons are interacting, give rise to many other fascinating phenomena, like in terms of charge density wave and most insulators. And here comes an exciting part when these two combine, and this give rise to more interesting physics, which is like the fraction quantum Hall effect or fraction Chern numbers, magnetic Weyl atoms and Chern insulators. And this brings us to the Kagome lattices that actually serves an intensive platform to witness these two combined effect. And due to this, the presence of the unique geometry that it has of corner sharing triangles, which of some of the traits that in terms of geometry, it has inherited from the very known lattices, that is the honeycomb lattices or the triangular lattices, but they differ in the basis functions and many things, but it possesses more rich physics in the band structure. Looking forward to a simple 2D Kagome tight binding model of the Kagome lattices. So the band structure holds the flat bands and the Dirac crossing, the Wang-Hong similarities. The presence of this flat band in this lattice is itself very peculiar and interesting because it arises truly from the lattice. So from the electron, from the destructive interference that comes from the electron hopping of the lattices give rise to these flat bands. And this is just one side of the story. These features that we see in the Kagome lattices further become more interesting when we include spin orbit coupling. And that results in the degeneracy lift around the band crossing point and give rise to Berry curvature, the source of Berry curvature, resulting in anomalous Hall effect, and which has been recently realized in the one set of Kagome family, that is Fe3Sn, manganese, titanium, and these families that I have listed here. And other, you can say, spare of Kagome, where if we are trying to see the band structures, the Weyl similarity nearest to the Fermi level, it in turn leads to another exciting exotic phenomena that comes due to the electronic symmetry breaking in terms of charge ordering, spin density waves, and superconductivity. And it has also been recently seen in the vanadium-based Kagome system. So after getting a background of the Kagome, I will go to the class that I'm more interested is the intermetallic class of Kagome family, that is the Fe3Sn family. And this family has also gained a lot of interest in recent years because it allowed the tunability of the structure and the physics by just changing the stoichiometry of changing the stoichiometry of this. So we go from the three-dimensional to the two-dimensional. And when we see from the three-dimensional, we have a strong interlayer coupling of the Kagome family, where you have the Kagome layers, one over each other, which is laterally displayed. And when we reduce to the quasi-2D, we have a Kagome bilayer, which is separated by the hexagonal scandium layer. And further going to the two-dimensional, we get an isolated Kagome layer, which is well separated by the scandium layers. So this particular family actually gives, you can say, intensive playground where one can see how, with the dimensionality, the electronic and the magnetic properties changes. But moreover, what are the additional features which makes these family more interesting is the presence of the room temperature magnetism, the high Curie's temperature it has, the rarer free, which make them a part of family where it doesn't have the rare earth in it. And also additional presence, the term breathing come from the part where they have an unequal size triangle in the Kagome layer, which further breaks the symmetry of the system and also additionally modifies the band structure and magnetism, add more features to the band structure that it has, and also the presence of moderate Coulomb interaction that it has. And the recent seminal paper that highlights that how the correlation and the geometry of the system combines and induces the chances of fraction quantum Hall effects, which further motivates to study this system more intensively. And particularly, I have, in my theoretical investigation, I have chosen this three-dimensional Fe3Sn system. So
can you go back one?
Yeah.
So just to understand, so in this left system,
Yeah.
yes, so there is one layer which looks like a Kagome layer, or how do you assemble this Kagome layer from this structure which you showed top left?
So they have like one over other Kagome layer, which is laterally displayed.
So each layer is a Kagome layer?
Yeah, each layer is a
Yes,
Kagome layer. Yes. So there is a strong interlayer coupling of the Kagome. So it is more towards a three-dimensional physics. And in the two-dimensional, the Kagome layer is separated by the thin hexagonal layer. So we get an isolated two-dimensional, more real to the ideal Kagome system, where you can...
Which is isolated from the next one by this honeycomb structure.
Yes, yeah.
And this When you say breathing, what do you mean by that? Are these some funnel modes or what?
No, the breathing this terminology is given because in this Kagome layer, these triangles, they are not in equal size. So in that sense, it is.
But they are fixed. They are kind of like static.
Yeah, they are static. But
is there some structural phase transition in this system which happens at some temperatures where this unequalness pops up below some critical temperature as some kind of water parameter, or is that
it is there
the
in
structure
this?
They are
there.
The highest possible, more or less.
Yeah, as far as I know, it is there in this structure. Okay. Yeah.
If they are unequal, then shouldn't there be some Young-Taylor effect or something like that?
Young-Taylor effect, I think so. It is not that can be there because the studies is not being done much on how this structural deformity can lead to, but it is quite interesting to look into that case. Yeah.
What do you mean by Young-Taylor effect? I mean, you already have a broken symmetry.
Yeah.
Right? So what else do you want to do with it?
If you have some asymmetry, then there can be distortions of this asymmetry.
It's already asymmetric.
But that asymmetry can be dynamic.
But it's not, as we learned.
No, that's what I'm asking. Why is it not dynamic? Generally, it is dynamic.
It is not. It is structurally present in this. Usually in the ideal Kagome, the triangles are equal, but in this class, one see the triangles are observed to be unequal. That is further leading to an anisotropy.
No, I understand that they are unequal. But what I'm saying is that you cannot just say that. Let's say if one triangle is smaller than the other, you cannot say that the left one will always be smaller than the right one. Like it can be dynamically, like you can have some sort of, in that sense, it really justifies this breathing mode. I mean, which I sort of think that should come from this type of distortion. I don't know.
But yeah, it is quite adjacent. I don't think so. It is random. It is quite adjacent.
But what is the difference quantitatively between these triangles? Like 1%, 0.1% or something in the size of this structure or motifs?
In the percentage, like I don't know, but the bond length, if it is 2.52 and this is 2.59 angstrom, so not much.
But okay, but in terms of some effective hopping, it would be quite
1%.
It would make quite a difference.
Yeah.
It's more than 1%.
Yeah, it is more than 1%.
Or?
No, approximately.
Yeah. Maybe it's better if you stand over there.
Okay.
If you don't mind.
Yeah.
Because otherwise.
Yeah. Shall I proceed for?
Okay.
So these are the recent studies that are done on the 3D Fe3Sn, the experimental and the theoretical investigation that further points out what are the important features that has been witnessed through experiments, that they observe a presence of high Curie's temperature of about 743 Kelvin, a large in-plane anisotropy that it has, and also experimentally they have observed some kind of formation of magnetic vortices. And this in-plane anisotropy somehow put them in the back foot in the race of the permanent magnets, but there are theoretical studies that by alloying or doping, one can change the axis of magnetization from in-plane to out-of-plane, but still stabilization in terms of experimental is in the progress. And we also, this system also show high anomalous Hall effect and presence of Weyl nodes. So all these interesting characteristics brings us to may explore the system further in terms of theoretical investigation.
Sorry, may I ask some questions about all this? So it's a ferromagnet below Curie temperature.
Yes.
So all spins are collinear.
Yeah. Yes.
And this in-plane anisotropy is a particular direction in plane, or it's just an easy plane anisotype of
It's easy plane. I will get into it.
You will show.
Yeah, I will show about the magnetism. So in the few further slides, you will understand. So, like the questions have arising that what kind of magnetic alignment is there, which kind of, so so the system require answer to all these questions, that how the electron correlation impact the band topology and the magnetism, and what kind of magnetic interaction the system has, whether it is a long range or a short range interactions, and how we can relate the band topology with their magnetism. So with these broad questions, I did my theoretical investigation by doing the electronic structure analysis using using the ab-inito methods, that is DFT, DMFT, and DFT plus U, as implemented in the RSPT code. And then I did the band structure analysis, and further extracting the energies, I calculated the magnetic exchange interactions and did a comparative analysis of all these three methods. And so I will first try to go with my DFT results, and then how I proceeded further with the DMFT and the DFT plus U. So in the DFT result, these are the DFT results that I got for this system without spin-orbit coupling. So we can see in the band structure the presence of nearly flat bands near to the Fermi surface, which do not cover the complete Brillouin zone. It is half of the Brillouin zone that covers around -0.6 eV, that cover half of the Brillouin zone, and the other hand also we see nearly a flat band, not completely. And that is quite expected, because we have this three-dimensional structure which have a strong interlayer coupling, which do not allow the Brillouin zone to, do not allow this flat bands to present throughout the Brillouin zone. And we get on halfway of this nearly flat bands. And also along some of the path that is near to the Fermi level, we see non-dispersive bands along AL and like gamma M directions. And further analyzing the orbital projected band structure, we came to know that the dominant contributions of these bands are coming from the DYZ and DXZ orbitals, the majority and the minority spin channel. And this orbital selectivity has also, we are in line with the nickel indium Kagome system, where also they report the contributions of the flat bands coming from these orbital d orbitals here. And further also doing the orbital projected density for the scandium, we observe hybridizations of the bands which are near to the Fermi level to that with the d orbitals. So this shows kind of DP hybridization is observed in the system, reflecting the iterant behavior of the system of as it is a three-dimensional structure, which can further help us in answering that what kind of magnetic exchange interactions is being driven in the system. So then what happened when we include spin-orbit coupling, how the band structure modifies. So before that, we calculated the magnetic exchange, magnetic anisotropy, where we get a very high in-plane magneto-anisotropy of about -0.6 in plane. And along the plane, the system is nearly degenerate because the order is in the mu EV. And so we get nearly in-plane AB degenerate, you can say, spin. And we have a strong in-plane, which is in line with the experimental reported results that we have in the literature. Going to the band structure, how it modifies along the in-plane and the out-of-plane. So we see a clear difference that as we go from the non-SOC to SOC, we get band openings, the band opening at the points near the Fermi levels, which are the Weyl nodes as we compare to the theoretical reported Weyl nodes that were present. And we get the openings of the bands. And as we also change the spin direction from in plane to out of plane, what we observe, the band structure has also changed. We further see In the hard axis, there is a band splitting coming over. Additionally, with the band opening, that actually points out a very important phenomena, that how the electron scattering differs with the different spin directions, so along the different magnetization axis, which is one of the phenomena which is reported also in the two-dimensional chromium triiodide system, the giant magnetoband effect, where we see how the electron scattering differs with the different spin-dependent magnetization, which also shows in our system. Apart from this, we do not see any change in the flat bands or the positioning of the flat bands or anything else. After investigating the electronic structures, we did the magnetic exchange interactions. So before going into the results, I will briefly give an idea how I calculated the magnetic exchange interactions. So we use the Heisenberg-Hamiltonian for evaluating the magnetic exchange interactions, which works on the principle that the atoms has localized spins, and these localized spins actually interact with each other, giving rise to exchange interactions. So in the realistic system, one can have long range and short range interactions. So we can have nearest neighbor coupling or second nearest neighbor coupling and so on for the long range interactions. So this is the Heisenberg-Hamiltonian, where my Jij is my exchange coupling constant, which is sum over all the possible bond. And also there is a scalar product of my two spins in this expression. So the sign of the exchange coupling constant tell us whether there is a ferromagnetic coupling or the antiferromagnetic coupling. So the positive value means the system has a ferromagnetically prefers to have ferromagnetic coupling, and the negative sign corresponds to the antiferromagnetic coupling. So there are ways to calculate the Jijs. That one is we can calculate the total DMFT energies for the parallels and the antiparallel spins, and we take the difference, and one can find whether they are parallelly aligned or antiparallelly aligned with the positive and the negative value. The other method is using the magnetic force theorem, where we do not rotate the spin completely, but we perturb the spin with the angle of theta and phi. And we further, using the perturbation theory, we evaluate the Jijs with the expression of this, which is formulated by Wilkinson and Gaston in the paper, which I have cited here. And we have used this method to further extract the Jij as implemented in the RSPT code. So,
Sorry. So these spins are iron spins, right?
yes.
And how do you then take into, but I'm assuming that this effective ferromagnetic or antiferromagnetic interaction is, you get this because of the presence of the tin somehow. Isn't it?
Tin is not having that much strong magnetic moment. It's very less, around minus 0.11. So it doesn't contribute effect.
So in general, if I just have iron, then,
yeah,
like the interaction should be ferromagnetic, yes?
We cannot say like it can be, because the system can also have some kinds of frustration, as the geometry is, you can say, triangular. So one need to calculate the Jij interactions, and further, if we want to be more precise, is knowing whether it is collinear or non-collinear, one has to go beyond this approximation into the atomistic spin dynamics to completely say that there is no non-collinearity or collinear. So
basically, in the whole of your calculation, the effect of tin is just to determine the dimensionality of the system.
So tin is a heavy metal, so it's when we include spin orbit coupling, so it might affect the anisotropic part of the exchange interactions. So we expect some kind of effect coming from the tin. So in later slides, I will discuss. So this particular expression of Jij in the Hamiltonian modifies when we include spin-orbit coupling because the spin and the orbital channel combined. And it further extends from the isotropic, including the anisotropic part that include my first, that is the symmetric part of the anisotropic exchange, and then this third term is the antisymmetric part of the anisotropic exchange, that is the Dzyaloshinskii Moriya interactions, which is very much significant to understand whether the system has collinearity or not, because it tells whether the system has some kind of spin frustration or some kind of chirality is there in the system. And one can also get to know if the system has a center of inversion. If it is so, then the DMI becomes 0 in the system. So give a lot of information about that. So based on this methodological part, I will now show you how what are the terms that I have calculated for the Jij interactions, how I have calculated. So this is the unit cell that I for the Fe3Sn system. So I have calculated both the in-plane and the out-of-plane Jij interactions. Since the distance between the layers is quite comparable to the in-plane distance, so we expect a large contribution coming from the interplanar interactions, and there should be a strong interplay layer coupling. So we have evaluated both the in-plane and the out-of-plane with respect to the distance. So this is showing the exchange path, the path that I have taken for the first nearest neighbor interaction, that is according to the distance, is in plane, that is E1. And the second, according to the distance, is E2 path, which is an inter-layer interaction. And then we have E3, which is again my intraplanar interactions. And then so on and so forth. For fourth, we see an interlayer interaction between the two layers of two atoms of the Kagome, and E4 is also my interlayer interactions. And with respect to distance, this is how I calculated the Jij, and what we get is after this is the plot for the Jij versus the distance. And here we can see that we get a very strong positive value. The first corresponds to the exchange value for the first nearest neighbor interaction, then second, third, and fourth. So from the first four, that's clearly we see a strong ferromagnetic coupling is there in the system, and it is quite long-range interactions. We see that on the 11th neighbor interaction, where you see 2 points, where we see for the 11th neighbor interaction, if I look at this graph, this plot, this 11th neighbor interaction is one comes out to be ferromagnetic and another comes out to be antiferromagnetic. That actually tells that there might be some kind of frustration in the system, because for the same distance, we are getting the system want to be ferromagnetically aligned, and for the other, it tends to antiferromagnetically align. So further analyzing the plot, we come to know that for the larger distance, the system is having an oscillatory kind of behavior, which gives a reminiscent of about KKR oscillations. And also we saw from the previous band structure plots that we do see some kind of hybridization between the D and P, which can be also help in these, you can say, the exchange interaction, further making that. To actually verify a little bit on the fact that whether these KKY oscillations are there for the distinct neighbor, we plotted the Jij with the scale of cube, which gives us that it somehow oscillate with the constant oscillation for the distinct neighbor. Following the 3D, that is for the 3-dimensional, it is somehow obeying that thing. But having said that, a more quantitative theory of whether KKR it follows this thing further needs investigation in terms of finding the capillary vector for the Fermi surface.
I have a question about this coupling. So what is the accuracy of the calculations? So precision of determination of these values. What is this?
Accuracy. Yeah.
Accuracy. So that is what I said, that this is just the preliminary you can say, point that we have said that after, if we look at this scaling form, because RKKY, if it is three-dimensional, follow this expression of cos by decay by the...
Sorry, this I understand, but this without in a solid curve, you
Okay.
have these couplings which are calculated from DFT, as far as I understand,
Yes.
and there should be some accuracy of this calculation.
So we went because it almost decayed. So we calculated up to a very higher mesh value where we get a saturation of these JIJ's values. So it is quite accurate with them. What kind specifically you want to?
Just an error of these calculations of the couplings. I don't know, 0.1 MeV or 1 micro EV or something like that. Do you know some? Yes. Are you aware of some number for this calculation?
So in this case, you DFT to calculate the green function. Then you use the green function in your perturbation formula.
Yeah. Yes. So by the magnetic force theorem where we evaluate, so it has been done. But it is more on the coding part, which. So with inclusion of the SOC, we see that the isotopic and the JIJ that we evaluated from the non-spin orbit coupling is nearly the same. We do not see any difference from that, but we do see the presence of finite DMI interactions that is there. The value of the DMI interactions, if we look relative to that of the JIJ, is very small, is of the order like 1 or 2%, which does not allow like a spin tending, which do not favor that the system will have some kind of spin tending in the system, but it shows that some signature can be there if we further induce some kind of changes in the system in terms of doping or strain. So it gave us an idea about that the DMI interactions are present in the system, and the interplanar DMI interactions is more than we look at the intraplanar for the first and the second neighbor interactions. And further, by this, I would like to summarize the first part, that is of the DFT, that we see the presence of nearly flat bands near the Fermi surfaces. The band features are quite different. When we look at different magnetization axes, we see a strong long-range ferromagnetic ordering in the system.
What do you mean by strong ferromagnetic ordering?
That is, we have like a very higher value of the ferromagnetic coupling for the first 4 nearest neighbor interactions.
So you say that ferromagnetic couplings dominate.
Yes.
Okay.
Yes. So then we have also some finite contribution coming from the DMI interactions, which points towards some presence of some kind of chirality in the system.
Sorry, related question to this. I cannot calculate it from my head, but is your crystal, does your crystal have inversion symmetry or not, crystallographically?
Because of the breathing.
Because of the breathing down.
It is, it breaks this triangle symmetry. So how further we look at when we introduce the electron correlation in the system, how these features further modifies, what changes we observe in the magnetic exchange interaction, thus be able to change the easy axis of magnetizations. To answer these questions, we went beyond DFT.
So can you go to previous slide? So if you ignore the spin orbit coupling, you will reduce the DMI.
We do not have the DMI. It comes into picture when we have spin orbit coupling.
So the spin orbit coupling.
Yes. So when we go beyond so we went beyond DFT. I did DFT plus DMFT using SPTF as a solver and DFT plus U to account for both static and the dynamic correlation as implemented in RSPT. So a brief summary of how we go beyond DFT to DMFT, where we are able to go from a localized gas, delocalized electron gas picture to an electron interacting in a path, where we can actually take in account the fluctuations. And for this, we map into an impurity model. And for my case, I have used SPTF as an impurity solver, that is a spin polarized fluctuation exchange solver, which is a perturbative solver, and it is like an extension of the flex with the T matrix fluctuation, taking into account all the kind of fluctuation in the system. So these are the results that I got from DFT when I go to DMFT. So this is the overall change that we see in the density of states and the band structure. So we clearly see the effect of the correlation in the band structure in terms of finite, you can say lifetime ordering, that leads to band narrowing or near to the Fermi surface, the Fermi level. And also due to the orbital polarization, we see a shift of the near flat bands towards the Fermi surface. It goes from minus 0.6 to nearly 0.6, and also with a slight non-dispersive band that we see also come near the Fermi level for this DFT plus DMFT. And also with respect to the Weyl nodes, we see the shifts of the Weyl nodes which were there in the DFT has shifted a little down, and also changed position with respect to the high symmetric points. And to further analyze that, we expect in DFT plus DMFT that we have the Fermi liquid renormalization and the orbital polarization. To further investigate this combined.
So can I ask a question? So as far as I remember, you showed that when you have a ferromagnetic order, your bands, there are opening of gaps in your electronic band structure, no?
No.
It was from, okay, no question. No, that's the questions here.
So then we analyzed further just with the static correlations, where we do not see the effect of Fermi liquid renormalization here. Here only the band shifting that we see is coming from the orbital polarization, that the 3D band shift towards the Fermi level. But we do witness here also the shifting of nearly flat bands or slightly above to what we observed in the DFT here. And this actually shows an overall picture that how the static and the dynamic correlation impact our band structures and physics. So further looking at how the spin orbit coupling further modifies this band's features, we did the spin orbit coupling calculations, and here also we observed similar features that we saw for the DFT calculation, that we observed band opening of the Weyl nodes, and here we can see that the shifting of the Weyl nodes has been there when we go from DFT to DMFT and DFT plus U. So this somehow we speculate that the difference in the quantum Hall conductivity that has been experimentally that has been reported for the single crystal and the polycrystal, between the theoretical calculated value and the experimental value, might be due to this unaccountability of the electron correlation if we try to go with this DFT plus DMFT or DFT plus U and look at further investigating the Berry curvature, which has been modified, and the Hall effect can one can overcome the discrepancy that we notice in the literature. So
means DFT calculations, anisotropy is the input, right? You do not change the anisotropy. The angle, that means the triangle has different side, you put it the input, but we're not changing your calculation, right?
Not change in the calculation.
Right, because like you can have like relaxation if you change like chemical potential, then the triangle can be changed.
Yeah, that.
Do not merge the input.
Yeah, that we haven't done. Yes, that can be done in future investigation. Yes. So then we further analyze the effect of the correlation on my JIJs. And what we observed as we look at the density of states plot for the three cases, we see that the decrease of the exchange splitting can be seen in the structure that actually reflects the decrease in the magnetic moments. And so we saw the decrease in the JIJ exchange strength, and quantitative changes can be seen in the first nearest and the second nearest interactions. So we see a slight decrease in the coupling strength as we go from DFT to DMFT plus DFT plus U. And looking further to the SOC part, which is quite interesting when we see...
Sorry, I have a question about previous slides. So can you maybe provide some hand-wavy explanation why on the left-hand side we have more or less similar results, but on the right plot, green curve is very different from other two?
Yeah, so because it is a DMFT plot that we, this broadening actually signifies you can say the Fermi liquid renormalization, which comes into picture when we account from the dynamic correlation. So the effect of dynamic correlation, one sees this renormalization of the bands coming from DFT plus. Whereas DFT plus U just account for the static part of the correlation. So we see a slight change in terms of the shifting of the bands in terms of orbital polarization coming. And the effect of this on this comes from how the exchange splitting decreases and the magnetic moments modify. So we see a decrease in the exchange splitting when we go from DFT to DMFT. That leads to decrease in the, you can say, magnetic moment magnitude, and in turn leads to a slight decrease in my JIJ strength. So, but we get a lot of impact in the DMI interactions. When we include the DFT, DMFT and the DFT plus U, we can see it's strongly affected by the inclusion of this. And also further analyzing the directional components of the DMIs, we can see that DZ component is a dominating factor in this, which actually is in line with the Kagome lattices. In this case, this particular graph actually tells us that, gives us an idea that DMI is quite affected by the external perturbations that we do. And if in turn we introduce some kind of strain and doping, we can further actually modify our DMIs, and we can find the many complex spin structures in the system, and we can further modify the structure in this system.
How you will get more complex spin structures here?
Like if we are introducing like strain or doping in the system, so I expect that my DMI will be, if we introduce strain in the system, so we expect some kind of change in the DMI.
Yeah, but anisotropy will also change, maybe grow, and then it will hide complex magnetic structures probably here. Because as far as I understand, you don't see any like non-trivial, non-collinear spin structure in this particular material without any perturbations like strain or something.
Yeah, but like the experimental people have reported presence of magnetic vortices. So we believe like if we are able to account for all the defects, because if we haven't taken in what realistically the system has some kind of vacancy or something like that. So we expect some kind of structures in the similar what is being reported in the experimental magnetograph experiments.
I see.
So this is the kind of speculation that we can draw from this. So this brings to the concluding remark of my studies that we see a great interplay of the lattice geometry, correlation, and SOC in tuning the near flat bands towards the Fermi surface, influencing my ferromagnetic coupling and DMI, and also in turn influencing my band opening, the Berry curvature, and the hard, resulting in maybe changing the anomalous Hall conductivity and the presence of Weyl nodes along the different magnetization directions we observed. So the possibility for the future directions, which we suggest that there can be a possibility of the lift shift transition if we include strain or doping in the system. And we can go on with the analytic and understanding of the presence of the non-dispersive band apart from the which covers the large part of the Brillouin zone, what is the existence behind and the flat bands in this system, and how impact of correlations further modifies my band very curvatures. And the another field is to go for the dimensional crossover from the three-dimensional to two-dimensional, and how the strain modifies the magnetic and the electron topology of the system. So this study has been done in NCU Poland with collaboration and guidance with Professor Igor DiMarco and Professor Lignu. And this paper is under the minor revision I have just submitted in PIB and soon to be published. So thank you for listening and giving me the time for this.
Questions?
I have maybe one. So at the very beginning, you mentioned also other compounds which are more two-dimensional than the one you focus on. And what can you say there about the band structure as it comes from these such, let's say, similar DFT calculations? Will you see more profound lattice effects from flat bands?
So based on the literatures, in the 2D Fe3Sn system, people has seen a flat bands completely over the Brillouin zone because it is near to the two-dimensional limit. And in the quasi-2D, there is the presence of Dirac cones also apart from the presence of the flat bands. So that is also very interesting as we go to the two-dimensionality of the system. And
so in your future direction, you saying that you want to study the effect of electronic correlation on the Berry curvature.
Yeah.
But I thought that you have the DFT calculation already.
But like the present code, actually, we cannot calculate the Berry curvature and the anomalous Hall effect. But this results can actually tell us that there is a shifting of the Weyl nodes, and possibly if we can calculate the Vernier projection and then feed it into the other code, we can find that.
So the DFT code that you have only have the energy spectrum without the wave function.
Yeah, but it does not support this Vernier calculation of
So you said that you expected some large anomalous Hall effect. Why large? What do you mean by that?
Because the band opening is different when we go from the DFT to DMFT. This, you can say, the gap of the Berry curvature that we see is quite different that we move from DFT to DMFT. So we expect some kind of change in the anomalous Hall conductivity.
But the change in anomalous Hall conductivity, you need to see how the change in Berry curvature.
Yeah,
Not
so
the
that
change in
has
the
to
gap.
be investigated.
Can have changed a lot of the gap, but the anomalous Hall can change small.
Yeah,
Depend on the
that
curvature.
has to be, we expect that because we look at, by looking at the band feature that is different when we see. So we expect that the anomalous Hall effect will be effective for that.
Because like the form of the band structure can change by a lot. But it doesn't mean that Berry curvature change a lot.
Yes.
Because it depends on the total Berry curvature, not local.
Yeah. Yeah, that is the future thing that we look for, to find the band curvature.
Is that like conductivity measurement in this material? Is it like anomalous Hall conductivity?
Yes.
Is this?
So this is the paper that they actually calculated the anomalous Hall effect for the single crystal, and both theoretically and experimentally, they get some difference in that. And also other polycrystal.
So in terms of the RKKY interaction, do you have intuitive understanding why all these results like the DFT, DMFT, and DFT plus U, why all these results are so similar?
It cannot be related to, I think, so the RKKY right now. I think so. The similarity that we get is, we cannot say complete similarity. Quantitatively, they are different. We get a decrease in the strength of
So, but the
changes.
qualitative trend is is exactly same.
Yeah, but because I don't think so that will change much with the inclusion of correlations. I suspect.
You don't think that?
Yeah, maybe like we. Like for DFT plus U, if we take the double counting to be more localized in limit, so we get the band increase in splitting because the bands become more localized. So there we get a reverse effect that the GIJ strength increases. But the mechanism, maybe the mechanism behind these exchange interaction can vary from the system, that how they are being mediated. That it can be to double exchange or super exchange, that can differ in these methodologies.
More questions? No? Then let us thank the speaker again.
The output of your DFT code. What is the output of your DFT code? The result come out from